Today we'll be talking about the shopping cart Swerve, which is a relatively new type of drivetrain that we found is very useful for FTC.
So first, what is a shopping cart Swerve? So a shopping cart Swerve has the ability to move in all directions, so it is autonomic. It has two motors and 2 degrees of freedom for each of the pods. The pod rotates and the wheels spins off center from the axis of rotation. So this allows the pod to move perpendicular to the way it's facing. Also, in order to make the Swerve kinematics work, the wheel tangential velocity needs to be the same as the module of the pod's rotation, the velocity of the pod's rotation. So basically, in this case, the speed that this edge travels whenever it's turning like this must be the same as when the wheel spins like this. So that's just one of the requirements for to make a shopping cart Swerve. Also, in order to do the power transmission, you can use a differential and a coaxial, which makes it really easy to power the motor or power the module from up above using pulleys. To make it usable in competition, you need 4 omni wheels on each of the corners to make it balanced, and you use 2 Lamprey absolute encoders to track pod rotation instead of 4 motor encoders, which with odometry would not be acceptable. So let's go into the physics of the way the shopping cart Swerve works. So by spinning the module, we give a tangential force to the ground. So this is when we move off center. The wheel is off, it's rotating. So there's some displacement going on whenever you turn, and that's how we get perpendicular rotation. And in order to move forward with the reference frame of the module, you just have to spin the wheel and it'll move in that direction. So this gives the module the ability to move in any direction, so it's autonomic. In order to program this, you just need to get a 2D vector representing desired robot-centric power. Then you just have to rotate it by the heading of the module. This is fairly straightforward. And from here, the x-coordinate represents the velocity that the wheel needs to spin, and the y-coordinate represents the velocity of the module. So from here, since we use a differential in our situation, we would just have to calculate the motor powers with the differential, and we just have to make sure that all of our motor powers are under 1, and we are done. There are no PIDs required because it is all just vector math. It's just each velocity for each of the modules corresponds to one and only one set of motor powers.
Just more specifically, there are no PIDs needed in making the module itself turn, but in order to get to a desired position, you would most likely need PIDs. So some benefits of the shopping cart Swerve versus Mechanism is that it has better acceleration overall, better top speed, and better traction. So similar to the benefits of a regular coaxial Swerve. What makes it better than a coaxial Swerve is that there are no PIDs, as we talked about earlier, in the pod rotation, and you don't need very high loop times. So basically, you can move instantly, almost, in all directions with the shopping cart Swerve. So the pod can rotate off-center. The wheel can rotate off-center to the pod spinning, and you don't need 4 servos, 1 for all the pods. You don't need any servos at all for the drivetrain. It's just 4 motors.
Yeah, it's kind of just a hybrid of differential and coaxial Swerve. So let's talk about the drawbacks of shopping cart Swerve. First of all, it is obviously more complex than a regular mechanism drivetrain, and due to the differential, we may not get 4 motors of power for all angles. So let's say if we want to move in some direction, like 45 degrees, only our differential math would only give us 1 motor power of velocity. One motor will be set at 1 power, and the other motor will be set at 0 power. So this means we'd only get half a motor power of wheel spin and half a motor power of rotation spin. So this usually isn't a really big issue because of the momentum that our module has whenever spinning. So that's because we're spinning at high RPM. And Another drawback is that the pod size is larger than Mechanism. So here I have a 72 millimeter pod size, and it's the module here sticks out of it. So in order to make it not stick out, you need at least 100 millimeters of pod width. This is significantly larger than Mechanism, which you can make it have 48 millimeters of pod width. And due to the low ground clearance, it's pretty difficult to adapt for terrain. And because the motors are mounted up high, it has a higher center of gravity. That's it. Yeah. Do you have any questions?
Why did you offset the wheel from the center of rotation?
That's what allows us to actually move perpendicular to the orientation of the pod. So let me explain that. So in this case, okay. So if we were to turn this module, you see how at the limit of where we only rotate it by a small amount, this wheel only moves perpendicular to the module is facing up, but the wheel actually spins or moves to the side. So we can instantly move the swerve that way, or the module that way, just by turning this module. It's like the way your wheels work, each one of your wheels, like on your chairs, they have it's basically a shopping cart swerve. So if you move that around, you'll be able to see that you can move in all directions.
All right, any more questions?
Yes?
Are we able to go closer to go get after you?
Yeah, sure.
All right, we have one question online. Lucas asks, what motors and gear ratio would you recommend using?
So for our drivetrain, we only needed 8 pounds. So we decided to go with like a 700 or 9.2 feet per second. I wouldn't really recommend using that for an actually like 20-pound robot. I'd maybe recommend an 8-to-1 or an 8 feet per second swerve drive. And just, I use bare motors. It's
Yeah,
just a
so
bare
we
motor
use
reduction.
4 bare motors and then 9-to-1 reduction.
All right, any more questions?
What cost? This is I think our cost went around to $1,100. That's motors, axon bevels, side plates. We metal 3D printed our some gears and shafts with JLC PCB, so that was another cost. Yeah, I think that's it.
Yeah.
So $1,200 total.
All right, any more questions? All right, let's hear it for the Roboplayers.